Fundamental Theorem of Calculus Part 2. Part 1 of the fundamental theorem says that we can use antiderivatives to compute definite integrals. Part 2 turns the relationship around. It tells us that we can use the definite integral to construct antiderivatives. Now, to state the fundamental theorem Part 2, we introduce the area function, which calculates for the signed area from a to x. Now, the area function has a lower limit of a and an upper limit of x. And in essence, we turn the definite integral into a function by treating the upper limit x as a variable. And note that a of a is equal to 0 because if you plug a into our upper limit here, it will give us lower and upper limit of a. And as we know from one of the properties of definite integral, if we have the same lower and upper limit, it will always result to an answer of 0. Now, the FTC2 states that this relationship always holds. The derivative of the area function is always equal to the original function. And to write it more formally, we have d over dx, the integral of ft over dt, our original function, and it will always become our original function. Okay, now let's look at an example. So example 1 here, we have our area function, and it is equal to the integral with an upper limit x, obviously, and a lower limit 3. And our function is t squared dt. And this one's already calculated for us. We simply plug in our upper limit in, and we plug in our lower limit in, as we know from FTC1. And we will come to the answer 1 over 3x to the power of 3 minus 9. And to find the original function, we simply find the derivative of our area function as we just calculated here. So we find a derivative of 1 over 3x to the power of 3 minus 9, and it comes to x squared. And this does prove that the FTC2 is in fact correct. As we can see here, we came back to the original function, x squared, and we know that we simply plug in the upper limit into the function. So instead of having ft, we would instead have f of x. And here, instead of having p squared, we came to the answer x squared. So we do know that the FTC2 holds true in this case. But now let's look at a more complicated one. So this one, we have a lower limit of -2, upper limit of x squared, and our functions is sine t dt. And this is something that we call a composite function because it does require us to integrate chain rule. So our area function here can also be written as g of x squared because we have an exponent in our upper limit. And because we have an exponent in our upper limit, when we find the derivative, we not only have to find the derivative of the integral of sine t, and then find the derivative of sine t, we also have to use the chain rule to find the derivative of x squared. So we write it like this: a prime x equals g prime x squared times the derivative of x squared, which would give us the answer sine x squared times 2x, and that is also equal to 2x sine x squared. And again, we pretty much just plug in x squared into t here, so we get sine x squared, but this time because of the exponent, we do have to find the derivative of the upper limit and times it by the function. So it will be 2x, and again, we come to the answer 2x sine x squared. So we can't forget about the exponent. When there's an exponent on the upper limit, we always have to use chain rule. That is something that a lot of people might forget, so it's very important that we remember that. And yeah.